Hello, everybody. Welcome. Glad you could join us. As always, if you're a repeat guest, welcome back. Great to have you back. Good to see some familiar names in the familiar names in the chat. And if you're new, feel free to say hi, introduce yourself if this is your first time, or if you haven't chatted before, feel free to tell us hello. Also got a little bit of a warm-up question today before we get to our gravity simulator. My warm-up question is, how much do you currently use AI? And I would say factor in your enthusiasm. Like, factor in enthusiasm in terms of your use. And I would say we do a lot of these sorts of questions. So let's go 0 to 10. Eight, PC, okay, good. Yeah. 2, 0. Zero from Mark. Okay. Ours only a 3. A lot of 4s, 5s, and 6s. I like that. I like our distribution. It's pretty broad. And I think that's pretty indicative of the broader population. I would say I'm probably an 8 or a 9, frankly. And I would say part of the reason why is because for building something like this, it's amazing for helping us make things faster, as well as to try and help me make my teaching better. So it's a pretty exciting, although terrifying time to be in education in general and to be in in-person education when we have to rethink everything that we do in terms of how we create really good experiences for students. So it's exciting to have to rethink that. But it's certainly going to be a lot of work too, but that's where I think maybe the AI can come in handy. I mentioned this because I did want to give you a preview of what we're hoping to build out here soon for our course. A lot of courses have, or a lot of websites these days have chatbots that are kind of built into the website. And I'm currently working with a team of some students, and the students are like expert designers and students who are really strong at how humans interact with computers. So we're trying to make something that eventually will be connected into the entire website to be kind of a real-time tutor to help you go through this. And you'll even see we added a little bit of a feature over here to show for your own local machine how much you've been able to complete, or, how many of these pages you've viewed, so you can see your current progress. And BZ, I agree. Chatbots on websites are generally not particularly helpful. And so our question is, how do we make something that's helpful? And I know we've had a few folks who even participated in interviews with our HCI team, which was exciting. And if you were one of those folks, thank you very much for doing it. And that sentiment that you have, which is that a lot of the default chatbot on a website stuff is really not particularly good these days. Now, that might not age very well, but I know that there was a lot of skepticism around this. So we're going to try having something that, over time is going to grow and evolve, and hopefully it's going to be good. One of my favorite posts from the other day was somebody was using the chatbot that was built into the Chipotle restaurant website, and were using it to ask Python questions about how to answer their data structures homework, which I thought was pretty intelligent. Like that way I don't have to pay for a paid certificate or paid subscription. So don't try to use our AI chatbot to order a burrito, but when we roll this out, we're hoping to have a real-time tutor that will have the same sort of voice that we try to present we try to give this sort of like warm, welcoming engagement that we have, and as well as some of the other stuff that we have. So one of the things that is probably going to be necessary for us to have a successful AI integration is that the bot, of course, has to love prediction markets, and stuff like that's really important too. So actually, I realized I had a link I was going to show you. Kalshi was in the news, our favorite website, and sort of informal favorite website of our platform here, was in the news recently because they enforced a very clear policy that they had about the exit of the Iran leader, and did not pay out some people who were surprisingly angered by that. But enough on them. Coming back to our site, I've posted some starter code in the chat, and you can also get it from our code along page. And so that's what we're going to use tonight. I'll set it up here momentarily. Yeah, the really dark outcome here is that I wind up being replaced by an AI simulation of myself, who's just 40% nicer and 30% more amenable to getting prediction market sponsorships and all that good stuff. But we're not quite there yet. So until then, there's still some life in this body, and we're going to do it as a human endeavor. A couple more course announcements. We had our first Roslyn stream last Thursday, and we're going to keep doing these Thursday mornings at 11 a.m. Eastern. It was cool because we had a bunch of folks that we don't typically have in our live streams here. So if you're watching this after the fact and you were there live, great, thank you. Please feel free to come join us in those. I'm going to try and make it through like all of the problems in the bioinformatics stronghold on Roslyn, and we'll see how that goes. And yeah, meanwhile, we're kind of streaming this once a week for now, and our projects have started, which is exciting. So we'll have another project cohort at some point. If you're still catching up on some of the part 1 stuff, that's okay. We'll also have a new set of projects that'll roll out as we continue going through part 2. That's based on some of these more advanced topics that we're going to see. So we won't have those quite yet, but we'll have new cohorts both for part 1 projects and for part 2 projects for our Philomath subscribers. And then the final course announcement I would say is we have autograders and the ability to get a certificate for completing our check your work exercises as well as the practice exercises that we have, and we've released that. So this is now on Cognitera, and I'll just throw a link to that in the chat here. You will have seen that if you're on our mailing list. I sent a message around about that earlier today. So if you're not on our mailing list, there's a link to that in the description. That's the best way to stay on top of everything that we're going to do. And we've got some big stuff happening that's going to be coming down the pipe. So stay tuned for more about that and some of the other content and courses that we're going to be able to start having. But no news just as of yet on that. And then I guess the final thing I would say is we're going to be starting a new chapter next week. So this we'll be pushing it out to the website later this week. In the meantime, if you want to get a head start on learning about algorithms for evolutionary trees, which is going to build on what we are doing here with object-oriented programming, you can check out our ebook. So our subscribers have access to that. It's also on Gumroad. I think we have a link to it in the description. But tonight we're going to build our gravity simulator. So you see it, we have check your work there. And I have the our starter code that we have, and I've downloaded it and put it into a gravity folder in Python SRC. So we'll get started there momentarily. If you don't have the starter code, again, it's in the pinned comment, and you can grab it there. I've just got main.py up. I'm going to walk us through here momentarily. I'm going to show you all of the different files that are present here and how everything's going to be organized. In the meantime, I think we're about ready to start. So let us know if you have any questions. Say hi in the chat, and we'll get started here momentarily. As always, please like and subscribe. That helps a lot. Join our mailing list, as I said. Join our Discord. We're going to have a lot more information coming. But for now, we've got a gravity simulator to build, so that's what we're going to do. All right. So to get started, you will see that I have our starter code, and it is a gravity folder that I've placed into the Python SRC directory that we've been working with. I'll walk you through a little bit about what is contained in this folder. So the first place we should start, this is all about object-oriented programming. And the first place I'm going to start is in our datatypes.py file. So I've already produced our object-oriented design for this, which mimics what we do in the preparatory reading that we have associated with this on our Programming for Lovers website. We have 3 different object classes that we've defined here, and we're using these data class ways of defining these classes. So this is a way that's going to simplify things down. We get that constructor function as well as the representation function built in, and the way in which we define our object classes is going to seem very generic. So we're going to have, for example, an ordered pair class, and an ordered pair simply represents a coordinate pair xy. Of course, we could also represent this just as a tuple, but that's not something that we're going to do. So I prefer, in this particular case, just representing an ordered pair as an object, and that object has an x associated with it, as well as a y. And if you don't specify what that x and y need to be when you define the object, then we're going to start them off with default values of 0. We also have a body class. Now the body class is going to represent like a celestial body or something that's under the influence of the force of gravity. And we have a lot of attributes associated with this body. And you might imagine we could have a lot of different things here, but I will specify that we have a name, which the default name is just going to be unnamed, or we could have an empty string. We have a mass and a radius, and these need to be in SI units, so our mass is going to be in kilograms and the radius is going to be in meters. We'll set them to values of 1 by default, but when I set these for a real example, so we're going to do the moons of Jupiter and some 3-body simulations, I'm going to read them in from file, which is the next thing I'll talk about. We also have red, green, and blue, and these allow us to assign colors. So we have the red, green, and blue channels, which are integers that are going to range between 0 and 255. And finally, I have position, velocity, and acceleration, and all of those break down as ordered pairs. So the position is some point we're going to do a 2-dimensional simulation. We could easily do a 3-dimensional one and extend our work here. And if you want to do that and post the result of your work to our Discord, by all means, go ahead and do that. It will be harder to understand a 3-dimensional visualization than a 2-dimensional visualization, though. And so everything here is going to be on a plane. And I think we're going to see some neat simulations just if we do that. We have a position ordered pair, a velocity ordered pair, and acceleration ordered pair. Velocity and acceleration are going to be represented here as vectors. So the acceleration is a representation of the force that's being acted on this body. And the velocity is sort of the speed and direction in which it's traveling. So both of those things are components. So we'll have a component in the x direction and a component in the y direction. And you'll note, you may remember from last time, when we work with data classes in Python, we would love to just specify that this is an ordered pair like that. And maybe we specify it as 0.0, 0.0. So it has default value, something like that. Although it already gets those defaults. So we don't even need to do that. Unfortunately, when we're working with objects and we make an object an attribute of another object. We're not able to do that. And so instead we have to have this very Pythonic, which means annoying, way of representing this by saying we have to import field from data classes and then have field default factory equals ordered pair. So we have seen this already when we started working with data classes. This is not going to be a major barrier to us working with data classes, but it just makes everything 14% uglier. Everything else is going to be fine. And we have one more class, which is a universe class. So the universe is going to contain a collection of bodies, which we're going to just represent as a list of bodies. And that will be able to track what are all the objects that are in the universe. Maybe there's 4, maybe there's 1,000,000. Then we're going to have a width of the universe that represents how wide this universe is, in this case in meters. And the default is 1,000, so we're probably going to have a much bigger universe than that in practice. And then we have a gravitational constant. So this is the actual gravitational constant that's been identified as the constant associated with the force of gravity. We're going to say a lot more about that here when it comes time to actually implement the physics side of things. So this is not so much a physics course as much as a programming course. We have a primer on some of the physics that you can check out on our website. I will show the computer science side of things where we implement that primer and implement that engine of physics operations that we need. And you can always refer there for more details. I'll say a little bit about how everything works as we go through, but it won't be as in-depth as what we have on our site. So this is the overall data organization, and I think it's quite, a good practice to have here is to make sure that how you organize your data is, in fact, pretty intuitive. The question I would ask is, why is it, here's a question for you, why is it that with this collection of bodies, I do the same thing that I did with the objects? So why is it that when I specify that a universe has an attribute called bodies, that needs to be a list of bodies, then when I give it a default value, I still have to do this field default factory equal, and then the type of the thing that I care about, which in this particular case is a list. Why would I need to do that for a list as well? Is there a short explanation for why this might be the case? Well, certainly it's the case that if I were to specify just an empty list, then yes, everybody would get the same empty list. So every universe you would have would get the same list, and then if you appended to that in one list, it would append to it in all. So any universe that you would create would get tied to the same collection of bodies, which would be horrible. Tom's a little closer and says it's because lists are passed by reference. That's close, right? With things that are passed by reference, we have usually another fancier word for this, though, in Python, because it's going to turn out, when we see what we talk about next time with object-oriented programming, everything in Python is technically passed by reference. But some things are passed by reference in different ways than others. So even though I've said, some things are passed by value, that's kind of not the full story. And we're going to get to that finally next time. The right answer here is that, like objects themselves, lists are mutable. And so if you have something that is a mutable type, so an object falls into that category because you can change it when you pass it into a function. List is the same thing, and if we had a map, we would have to specify this in the same way. But if you have a basic built-in type, like a float here, and in here, or I think we have the name, which is a string, all those built-in types which are immutable, they're all going, which we think of as pass by value, all those are going to be fine. So if you have an object, a list, or say a map, these are the types of things that we've seen that are mutable. And in those cases, you're going to have some trouble. So it all can be fixed by with this field default factory equal to the type that you care about. The next file I would show you is, let's take a look at custom.io. And to look at custom.io, I want to point out that we have some initial universes represented in our data folder. So the first one I would point you to is Jupiter moons. Now, we know plenty and could easily write the functions that we're going to need in order to read in a file like this and store it as a universe. Do we really want to do that, especially synchronously? Absolutely not. So this is not something that I want to do, and I will appeal to some starter code that we have in our custom.io file, because we know, I think, enough about parsing to appreciate how it works and to be bored by it. And so I'll give us some starter code for that there. I will point out, how is it that these files are always organized? Well, in each particular case, we have a few different things. So the first two lines specify the width of the universe and then the gravitational constant that we want to use. So when we read this in, I'm going to use the standard gravitational constant and then the width of this particular universe in meters, which this is going to be Jupiter as well as 4 of its moons. And I think it's got a couple dozen in reality, but we're going to have 4, the first 4 that were discovered by Galileo. And so we're just going to need a universe that's as wide as it needs to be to hold all 4 of these moons inside of it. Then you'll notice each body is represented by a collection of attributes. So you have the name of the body, which is always on a line that starts with, this greater than symbol. Then you've got the color as an RGB code. Then you have its mass here in kilograms. So we can read out a number like this. This just says 1.898 times 10 to the 27th. That's what that E plus means. Here it's times 10 to the negative exponent 11. And then the next line is going to be the radius, which in this case is in meters. That's going to help us draw this. And then we have its position within this universe. So Jupiter is going to be in the center. So these values are half of that. And its initial velocity is going to be 0, 0. It's not moving. For each of these other moons, we have a color associated with it. We have its mass. Notice this is quite a bit smaller than the mass of Jupiter. Then again, we have its radius and then its initial position. And if we know this, we know how far it is from Jupiter and we know it's orbiting, then we can compute its initial velocity as well. So when we look at this and we see 0, negative 17,320, this is in meters per second. And so we can think of this, if depending on how we're going to draw this when we orient it. But if we're thinking about Cartesian coordinates, we think it's not doing anything in the x direction, and then it's moving downward at 17,320 meters per second. And that's different from Europa, which is actually moving to the left, Ganymede, which is moving to the right, and Callisto is moving up. So we've placed these moons so that they're in orbits that are kind of a little bit far apart from each other. And what we would like to have is a function that reads this in from file and creates a universe object for us. I'll also point out that we have a few other never before observed configurations of 3 bodies. So one of the motivating applications that we see in this chapter is the idea that no one has ever produced a precise mathematical formula where if you give 3 heavenly bodies and their initial velocities and so forth and a time, you would be able to quickly determine exactly where they're going to be after that certain amount of time. So this is still very much an unsolved problem, but it's not an unsolved problem from the perspective of simulation. So we're still very much able to produce a gravity simulator that will take these initial conditions of these 3 bodies and see what happens over time. Now there's some weirdnesses here. For example, the gravitational constant is set to be 1.0 here, and the reason why is because the physicists are showing us that this is a theoretical simulation. And so they just set this gravitational constant to 1. And the reason why is because you can get the same simulation with some other values of, x and y as well as initial velocities, but they become much larger and unwieldy. So this makes sure that we keep our velocity values small. So that's nice. And what we have in Custom IO is the ability to read this in from file. So we've got some files that I want you to think of on a very high level, which is they perform quite a bit of some checking on the file name and making sure that we can open the file. And this is sort of some additional parsing that goes on behind the scenes just to make sure that there's not any extra space on certain lines and so forth. At the end of the day, we're able to specify a file name, and then from that it reads in from that file and produces a universe object. So as it ranges through, it goes through and identifies the width and the gravitational constant and the bodies and so forth. And we could also, we'd be welcome to split this out into multiple functions. As you go through the file, what happens is at the end of this process, you produce for each line of the collection of lines of the file, you make a body where its name is equal to whatever name you've read in, the mass and radius are equal to whatever values you've read in from the file. So let's leave this to the parsing side of the code. And we've got a little bit of modularity here in the sense that we also parse an ordered pair. We have a separate function to parse RGB values and so forth. So we wind up with quite a lot of code, every single line of it pretty boring, but we're going to get to use it at the end of this. So I want to focus on the things that matter, and that means that we're going to write our engine for this in gravity.py. So we'll nearly get there, but I want to point out a couple of other things that I've given us. Number one, we have animate.py, and if you followed us before, then this is going to be a very similar file. It's the exact same file that we've worked with before. That's going to take a collection or a list of pygame.surface objects, and then it's going to also take where it is that you want to draw these things, and it's going to produce an MP4 taking all these snapshots of the system that we've drawn and producing a video out of them. So we will use this in main because this is the same code that we've seen in the past. And then we're going to have some drawing code too. So we could probably do an entire code along nearly on drawing. And I want to point out that how this will work is, again, thinking about everything in terms of inputs and outputs, and fortunately having doc strings for what we're going to do. We have a collection of universes that we start with. We have the number of pixels wide and tall. So we're going to have a square canvas. So we're going to say how many pixels wide and tall should that square canvas be. And we're also going to have something that we haven't really seen as of yet. And I'll go ahead and say exactly what it's doing, which is that what we don't necessarily need to do when I simulate the force of gravity is to draw every single snapshot that we produce when we simulate the system to a canvas. And the reason why is, well, why don't I ask you a question about that? Why is it that I would not necessarily want to draw every single snapshot that I make of the system from the perspective of measurement of where is it that each of these heavenly bodies is at this point in time? Why is it that I wouldn't necessarily want to draw all of those to a canvas and then produce a visualization of all of them? Because that seems like a reasonable thing to do. Why would we not do it? Output would be too big. That's a good answer, sure. Maybe the resulting MP4 that I get would be too large. It's certainly going to save time. So if we know that drawing takes a little bit of time, I'm going to run my simulation probably for, 10, 100,000, a million different snapshots. There's one other critical point here, which is when I simulate gravity, I'm going to simulate gravity for a very small unit of time. That's good. That means that I'm frequently updating all of the attributes associated with each object. That means I'm getting as close as I possibly can to continuous estimation. So the smaller unit of time that I use, the more accurate my simulation is going to be. Once I use a unit of time that winds up being tiny, we might not see anything in the system move for many frames. So what you would wind up seeing is an animation that produces a very, very slow simulation. Just as when you look up in the sky, you don't see many things move very quickly. We don't want a simulation that has this same issue. So we have an enormous file, and then it's just like watching real gravity. We want to speed this up. And so I'll use a tiny unit of time to simulate the force of gravity, but then when I draw this, I'm only going to draw a frame every so often. So the current frame or the current universe that I'm working with in what I'm calling time points needs to be divisible. So its index needs to be divisible by the drawing frequency in order for me to actually draw it to a canvas. So in particular, I'm going to say when I% drawing frequency is equal to 0, you divide it and you don't have a remainder, then we're only going to draw a frame then. All right, so we do a lot of checks. We make sure everything here is in good shape. And then what we're going to do is we range through, and for each time point, I'm going to produce, if I is divisible by the drawing frequency, then I'm going to append the current canvas. And the current canvas is produced by calling this draw to canvas subroutine. So I pass all of the work, in essence, to this particular subroutine. And there's one extra little thing here that I'm not going to get into the hardcore details of. This is only from the perspective of making our visualization just a little bit pretty. Is I also am going to have a collection of trails. And all the trails are going to represent, you can dig into this as much as you like, but what they're going to represent is the ability to remember where you've been, which is nice. It means I'm going to be able to see the current position of the body, but instead of just a bunch of circles flying around, I'm also going to see where they came from. So you'll see the shape that they trace. That will be very nice for visualization. But the draw to canvas function works, like when you look at it, you'll see it looks pretty similar to how we might imagine it's going to look. We set the current color, which is to say, what's the current body's color? There's a little bit of needing to draw the trail here. And then when we draw the body, we say, what's its current position? And we scale it. So we're converting its position, which might be in like millions of meters, down to pixels. And this is the exact same thing that we've seen before when we worked with automata. We needed to figure out exactly where to place this thing on a canvas. So that's about it, about everything that I wanted to say in terms of drawing. One other question I guess I would have for you is, at the end of the day, this is the line that says on the surface, with these RGB values for the color and this particular radius at this position, I want you to draw a circle. So draw the circle that has this center and that has this radius. And you'll notice that I have the line here that the radius is equal to the maximum of 2 and the int of b dot radius times scale. So b dot radius times scale is just allowing us to scale down and know how big the radius needs to be when I draw this thing to the canvas. Why do you think, here's my question for you, why do you think I did the maximum of that and 2? What is 2 doing here? What purpose does it serve? Great, AKB, less than 2 would be too small to see. So if the radius is 1 or 0, that would be a bad thing. And you might imagine, all right, well, it could be possible that as a result of the scaling, we might scale everything down to where the body that we want to draw winds up having a value when we produce this that is like 0.3. And when we take the integer of it, it winds up having a radius that's equal to 0. So we wouldn't actually be able to see it. That is the exact thing that will actually happen when we draw the Jupiter moons. So without this line, when we run our simulation, and I always have enjoyed tricking students with this. Sometimes I thought I'll try to be nicer to you, but when I've taught this demo in a class, I won't have this. And then when we produce the Jupiter simulation, everything is working perfectly, but all you see is Jupiter in the center, and then you don't see its moons. And the reason why is because Jupiter is so much bigger than its moons are, then that at the end of the day, in order for Jupiter not to be enormous, you want it to be like a reasonable size, but then this is going to shrink all of its moons down to so tiny that you don't see them. So when we produce that Jupiter moon simulation, I want you to remember the moons are much smaller than they seem compared to the size of Jupiter. It dwarfs them by a huge factor, but this allows us to make sure that everything that we produce actually is visible. So it's a nice little trick. All right. If you're curious about the trails, because I glossed over that a little bit from my perspective, that's just a nice visualization component here. That's not something I want to dig into in terms of learning how to solve problems. Take a look at it. Let us know if you have any questions on our Discord. Great. But in the meantime, I'm going to work on the things that I think are more interesting, which is to build a gravity engine for what we're going to do. And that gravity engine is going to be contained in gravity.py. I have a bunch of function signatures that I've already written, a bunch of doc strings that I've already written for us, because this is a bigger project, and we can appreciate all of this as we go through it. And we're still going to be thinking about inputs and outputs, but I'm not going to spend a lot of time doing a ton of type checking and validating all of the inputs that we have. That would bring us up to like professional code, which is something we've really focused on here. There are so many possible things to check here that I don't want to clutter the code too much. So instead, how I want to start here is with a simulate gravity function. And as always, we always start at the top of our function hierarchy, meaning I like implementing the function that's going to solve the problem that we're interested in. And the problem that we're interested in is to take an initial universe, which is a universe object. So it's an instance of a universe object. We have a number of generations, which here is an integer. And we have a time step that in this case is a float. And as a result of this process, I want to produce a list of universes. These are what I call time points in that animate.py file. And what they correspond to is a bunch of snapshots of the universe. Here is the case where I'm not worried about doing this only for a certain collection or things that are divisible by a drawing frequency. I want to simulate the force of gravity for a small time step as much as I can. So when I produce this, I'm going to produce the full collection of universe objects that in other places I called time points. And this is the highest level function in the engine of what I want to do. So again, start with the universe for the number of generations that we run and for the time step. Note this is also going to be very similar to what we've seen when we simulated, say, cellular automata. My highest level function, right, was going to say, what do we start with and what are the rules? And then what does that produce? It produces a collection of automata game boards. Same thing here. We have our starting point and then the parameters that we need, and we produced a list of universe objects. So we want to implement this function, and it's an easy function to write, as is the case for a lot of our highest level functions, because we always want to be aspirationally lazy. And in this particular case, that's not going, nothing changes there. When I implement this function, after I make sure that I perform my checks, I'm going to say that I want time points to be a list of universe objects. And we could start it as being empty, although really I know what needs to go in there initially, which is the initial universe. And then at the end of this process, way down here, that's what I want to return. So we'll create a list of universe objects, and then at the end of this process, that's what will fall out the other end. In the meantime, then, we need to range over the number of generations that we have. So range over all the number of generations and pass our work to a minion. So in order to do that, I'll say, let's have a range that says for I in range, starting at 1, going up to the number of generations that we see, plus 1. And as I do that, I'm going to say, well, what's the next universe down the line that I care about? I'll say next universe is equal to what happens when I update the universe of the current universe. So the current, and I could even specify that. I could say that the current universe is equal to whatever the previous snapshot was. So in this particular case, it's time points of I minus 1. And anytime I type I minus 1 as an index into a list, I need to be very careful. And remember, red alert should be going off to think, well, I want to make sure that this can never be -1. In Python, we're going to get very weird behavior if that happens. In other languages, we would probably rightfully get an error. But here's where I keep in mind that I starts its ranging at 1, so this will start at 0, which is what I want. And I will update this universe of the current universe. And then I'm going to give it the time step. So after this process, I'm simply going to say timepoints.append that next universe that I need. And that's my entire function. Of course, I could also take this and just put it here, and I don't need that current universe declaration, and we just have a couple lines in our for loop. And that's implementing this function. So as we've seen before, we can do something powerful just by taking the number of steps that we want to run it for, ranging through that number of steps, and peeling that particular parameter off and passing all the hard work to a subroutine that just focuses on the simpler question of, I have a current universe object and I have my time step that I care about, and how does that produce the next universe object down the line? So I've simplified this down from doing it n+1 times to just doing it 1 time, which is always helpful. So we now come to updating a single universe. We have the time step that we want to use, and we have the current universe object that I have. And I'll say a bit more about what I mean by this Verlet style update in a little bit. But again, we're procrastinating in a structured way. And we're going to apply the same principle here. So I want to implement this function to update the universe. And as we do this, I'm going to say, all right, well, how should this function work? What it needs to do is it needs to first create a new universe object. And that new universe object needs to have a specific collection of attributes associated with it. So if we think about, well, I've got my existing snapshot. I don't want to change that. Although from the perspective of rendering it, I could always render as I go. But this is the sort of thing that we've seen, at least from an introductory perspective, we don't tend to do this because, for example, once I have a collection of time points here, I can do more than just visualize them. I could do things like determine, how is it that the speeds of all these bodies are changing over time? What's the closest any two bodies get to each other? I could have the complete set of data associated with it. And if I do that in place, well, I'm going to muddle up drawing and data generation, which is something we've seen is not necessarily a good idea for, especially if you're a beginner. And also we're going to be throwing out data that might be useful. So what I'm going to do is I'm going to say, to update the universe, I have my existing time snapshot. And I want to copy over all of the attributes, so all of the bodies and the gravitational constant in that particular timestamp, that particular snapshot of the universe, and put them into a new universe. So we'll say new universe is equal to current universe. And you might wonder, this seems perfectly reasonable. Then we'll range through and say we're going to update everybody in the cloned universe based on the forces from the current universe. So what I will do is I want to range over all of the bodies. So let's range, I'm going to call B, say B. And I know that if I access universe or new universe dot bodies, that's just a list, and it's a list of body objects. So I have this nice, short, tight Python for loop that will range over all the bodies. And as I do it, I want to update the acceleration. And this is based off of the current universe and B. I'll explain what's going on here, but the idea of updating the acceleration is that I'm going to be updating the force of gravity that every body in the current universe exhibits on B or exerts on B. And I need to update the velocity as well. And here's where I'm going to have B. And I'm going to update the position too. And in each of these cases, I also need to specify the time. Okay. So the acceleration is not a function of the time because it's a representation of the force that the current object is being exerted on. In the case of velocity and position, though, once I know how, in what direction and by what magnitude the current body is being pulled by the force of gravity, I can then go through the process of updating the velocity and position based on that force. So this means that I need to know for how long am I going to apply the particular force or apply the outcome of this force. And in this case, I've got, I'm updating the velocity, and I'm going to need the previous acceleration as well. And I'm going to need the previous acceleration and the previous velocity when we update the position. I'll explain this here when it comes time to implement each of these functions. But for now, I'm going to say that the old acceleration and the old velocity are going to get set to what their current values are. So this is b dot velocity, and the old acceleration is b dot acceleration. Okay. Once I've got each of those two things, then I'm going to say they'll be useful when I pass them into the velocity and position functions. The previous acceleration is going to be useful, and note, I need the old acceleration because I've just updated its value. So it has already changed, so that's why I have set this. And the velocity at this point in time has changed too, and it's going to be useful here. So I use those previous values, which is why I pass them into this function. At the end of this process, what do? I want to return my new universe that I produced. So we start with the current universe, range over the bodies, figure out what the important fields are that need to change. So the color of the body is not going to need to change. Its name is not going to need to change. And presumably all this is handled by this line. And all this is well and good. There's just one little problem with how we've written this function, to take an existing universe and produce the universe corresponding to the following time point. What is the current issue with the function that we've written? What's wrong? Larry says there's only one of like 3 answers to all my questions about Python, right? So if you say mutable, it's probably a good answer. And in this particular case, yes, exactly. We'll talk more as we go through more object-oriented programming, but this does not create a new universe object. What it does is this establishes 2 names or references for the same underlying object. So it says this thing that you've been calling current universe, okay, I'm also going to be able to call that thing new universe. That's not good. In this particular case, it would be really bad, because what would happen is when we update all of these acceleration, velocity, and positions for each body in my new universe, it would also change the previous time point. And so that previous snapshot would have all of its values updated to the current ones, and you'd have a really big mess because you wouldn't actually see, when you visualize this, you'd say, well, why is it completely static? And why are these seem to be like final positions of the universe? And the reason why is because you would be dragging along the previous universe every time you did this. So not great. And as a result, what we need to do instead, I'll actually leave this line and say instead, we need to perform what's called a deep copy of the universe. And there are built-in packages to help us with this, but just as we've seen throughout the course, I like showing you that we're powerful enough to be able to do something like this. And then of course we can use these sort of built-in things later, but I want to explain sort of what would go on when we perform this deep copy. So I'm going to have a function here that says new universe is equal to copy universe of my current universe. And if I write this function correctly, this will ensure that I have a brand new instance of a universe object, and that all of the attributes of the previous universe or the current universe have been copied into that new copy. The question becomes, how do we write that function? And we can write that function, if I have my copy universe, yeah, I have it way down here, lurking in the bowels of my code. And this universe, or this copy universe doc string is easy to write. I'm going to establish that I need to copy over all of the attributes, but for this particular case, we know that the universe just consists of bodies, a width, and the gravitational constant. So deep copying a universe is a relatively straightforward task. In this particular case, I'm going to say, well, we've got a new collection of bodies, and it's a list of body objects, and it's going to start off as empty. And then I'm going to say for B in the current universe's collection of bodies, here's where I will say, let's take new bodies and append the result of calling a minion called copy body. So our subroutine is going to handle copying the body, because you would imagine, well, I know that a body object has a bunch of attributes associated with it, so let's instead pass the work of copying all of those things to a subroutine. And at the end of this process, remember, that's the only thing that's mutable. So when we have our list of bodies corresponding to the collection of things in the universe, that's mutable. But the other two things, when you look at them, are the width, which we don't want to change. So this is how wide the universe is, and the gravitational constant that we have. And presumably, we don't want the gravitational constant changing either. So I can go ahead and return a new universe instance. And I'm going to say that in this particular case, we have our new bodies, we have the current universe dot width, and we have the current universe dot gravitational constant. And we even could be more precise. So when we write it in this way, we kind of are assuming that we know that the order of the attributes that we have in the universe are bodies, and then width, and then gravitational constant. One of the things that you might have noticed is and we'll say more about this as we go through more object-oriented applications, is that when you look at custom.io.py, for example, and I think and we set the individual elements here, when you create a data class, an instance of a data class, and you set, here was the particular body that I have, you can actually set each of the attributes associated with that equal to what you care about. And that allows you to do it in any particular order that you like. So you don't have to remember that we usually put bodies, then width, then gravitational constant. What I do need to know is, what are those attributes? So here's where I will say bodies is equal to new bodies, and the width is equal to the current width, and the gravitational constant is equal to this. So that makes our code a little bit more robust. So we're ensuring that it is clear that we're setting each of these three attributes of the universe object that we have. Now, we've passed most of the work to a copy body function, and that's the function that we also should write. And here is going to be like your first writing of a deep copy function, and probably last, because it's not something that we really need to focus a lot of effort on. But what we can do is to say, in this particular case, I could go through the process of establishing ordered pair values outside of it, but actually I can just return a body. And then I need to say, what are all of the fields that I care about? Or what are these attributes? So its name needs to be something, its mass needs to be something, and so forth. And I want to make sure that I capture every individual thing that I have. So name, mass, radius, position, velocity, acceleration, red, green, blue. And in this particular case, when I set name equal to b.name, that's fine. Okay, so this particular assignment we've worked with. Why? Because this is a string. So when I set some string x equal to some other string y, it's not saying that x and y have the same name now, that it's one string with two different things. We've seen this going back to the very start of our course, which when you have a string on this side, this is a variable name of a string. Whatever you have on the right side of this equation is just a value. So if b.name has some string value, we're now setting the name of the new body equal to whatever the value is in the old body. The key point is, now that we've made this transition to object-oriented programming, here is where things can get a little bit weird and funky with assignments like this. So that's why when we copied all the universes, I made sure to make a fresh list of bodies and then set our collection of bodies in this way. Now, I'll go through and in the meantime simply say the mass is, again, a float. So for that reason, it's fine to have an assignment where we just use the equality like this. We need position, we need velocity, and we need acceleration. We need the radius is equal to b.radius. The red value is going to be b.red. The green value is b.green. And the blue value is b.blue. And now you see why we don't tend to do this. I'm going to add a comma there just for consistency. Python won't get angry. But I should establish these are ordered pairs. And they're, in particular, I'm going to create ordered pairs by saying, well, we need the position of b in the x coordinate, and we need its y coordinate as well. So here's where we get to see accessing for a given body. We use the dot to indicate here is the field that's associated with it. And it's cool to see an example of this being nested. So we have b.position, and then that is an ordered pair, which is an instance of an object itself, and I can access .x or .y of it. I can do the same thing now for velocity and acceleration. I want to be very, very careful when I do this, of course, to make sure that I remember to make sure that I establish this is a velocity and this is a velocity. If you don't, go have fun with forgetting to set like both of these to be accelerations. Instead, set that to be a position, and then watch what happens with your simulation. It's going to be pretty cataclysmic, but it will be fun. And that's our copy body. And that is our first and only foray into manually writing deep copies, because fortunately these days, programming languages will be able to infer that if I want to make a deep copy of something, even if I have nested objects and mutable things inside of it, I will go through and range and make sure that I make copies of every single last thing. So we'll see that as we move through object-oriented programming. For now, though, I want to point out, just as we've seen throughout the course, just because something has a built-in package or method of or whatever to do it doesn't mean we can't do it ourselves. Now we get back to working with the physics engine that we were making, and we can come back to where we were, which is implementing our update universe function, which is now complete, except for the fact that we've got to write our update acceleration, update velocity, and update position functions. So when we write update acceleration, we're going to get to use Newton's second law, which is exciting. Now, most of the time, Newton's second law is written with the algebraic manipulation of saying that it's capital F, the force is equal to the product of mass and acceleration. But we're going to write it, because we're updating the acceleration, in this way. So we're going to divide both sides of that equation by m to get that the acceleration is equal to F over m. And in particular, we're going to have an ordered pair that gets produced. So this will constitute what's the acceleration in the x direction and what's the acceleration for this body in the y direction. And the ordered pair there is going to represent the two components of that acceleration vector. And so we're still going to have that a is equal to F over m, but the component of the acceleration in the x direction is going to be equal to the component of the force in the x direction divided by the mass. And the same thing here. The y component of the acceleration will be the y component of the force divided by the mass. So we need to implement this. And as we've seen before, you're not going to be surprised by what I'm going to do, which is to delay writing the hard stuff for as long as I can. And in this particular case, I'll say, well, if I'm updating the acceleration, and I know that the acceleration is a function of the force, what I really care about is computing the force due to gravity acting on B as the result of all of the bodies in this current universe. And so I will say, well, let's take all of that hard stuff and put it into a force vector that I'm going to call compute net force. And it's going to take the exact same parameters. It's going to take current universe, and it's also going to take the body B. So I take both of my parameters that I have here, and I simply pass them down into the compute net force function. Once I've got that, now I get to apply Newton's second law, and I should say I'm applying it component-wise, meaning I'm going to look at the x direction, and I'm going to look at the y direction. So here, for example, AX is going to be equal to whatever that net force vector is in the x direction divided by the mass of the body. That's the force divided by the mass. And AY is going to be no different, except that I need to make sure that this is the net force in the y direction, still divided by the mass. And then as the result of this, I'm simply going to return an ordered pair constituting the x component and the y component. You might think, well, I haven't done a whole lot here, but I have in a certain sense, which is that I knew that I would have to apply the second law here, and I've done that, and I've replaced computing an acceleration with computing a force. So I made it just a little bit easier, and then I can look at the compute net force function and write that in turn. And that must be hard, right? It must be. So now we get to write compute net force. This is going to take a collection of bodies in the universe, and it also needs the gravitational constant, which is why I'm going to take the whole universe and give it as input. We're also going to have the single body that I'm saying, what is the force acting on this body? And then it's going to produce an ordered pair. So here is where you're thinking we must need to apply some physics and say, what is the formula for this force? But actually not really, because if I'm saying I'm looking at the universe of all bodies, and what I'm producing is a two-dimensional vector, which is this force vector that says, what's the gravitational force acting on the body over all of the constituent bodies in the universe? If that's the case, then what I want to say is I don't need to necessarily worry about the details just yet. What I'm going to do is I'm going to start with a vector that's equal to an ordered pair, 0.0 and 0.0. I don't need to specify that technically, because not only can I not type it, but x and y start off as 0.0 and 0.0 in our data types. But we'll start it with the default values and be very precise. And then here's where I'm going to say, let's range over all the bodies and determine the force acting on B. So I will say for the current body in the current universe, that's the input universe, dot bodies, that's the list of body objects associated with the current universe. As I range through this, I'm going to say, let's make sure that we don't compute the force of B acting on itself. That would be bad. So fortunately, we have a nice quick Python check here, which is to say, I'm only going to do this if the current body is not B, okay? And this is an amazing Python construction that you might think is not valid, but actually is. So you don't need not current body is B. You actually can just write current body is not B. And that's a nice way of checking, is the reference to this thing the same thing as the reference to this thing? Okay. So if those two things were equal, then you know that you're in fact at the body B. And here's where we'll say, okay, compute the current force of current body acting on B. And I will say, how will I do that? Guess what? Starts with an S, rhymes with an subroutine, and we're going to have current force is equal to compute the force that is exhibited on B by the current body. And technically we're missing one little thing, and I'll tell you what it is here momentarily. But once I have that force of that body, what I want to do is add it to the overall contribution. And if you do the reading that's associated with what we're working on here, you'll see that one of the nice things about splitting vectors or forces or accelerations or whatever into components is that you can add them by adding up the components. So I'm going to add the x values and I'm going to add the y values. So if I represent this force as it has something in the x direction, it has something in the y direction, I can simply take net force in the x direction and add to it the current contribution. The current contribution is current force dot x. The same thing in the y direction. I'm going to say net force in the y direction is equal to whatever it is in the y direction added to it. Then at the end of this process, I'm going to return net force. And I've saved all of the details. There is one little thing though, which is that when I compute the force acting on B as the result of current body, there's one thing I do want to remember about the universe, and that is the gravitational constant. So that will, when I get down to the nitty gritty of actually computing the force, I'm going to need to make sure that I say, I'm going to use this letter G to indicate that the current universe's gravitational constant is equal to G. And I'm going to pass G in as a third parameter to compute force. I'm just going to try to. So this will tell us, G tells us how strong is the force of gravity in this universe that we're working in. And it's actually not particularly strong in the grand scheme of things. So as we've seen in what's the default value? The default value is this 6.674 times 10 to the negative 11. So you and I don't really exert much of a measurable force of gravity on each other. And so you have to have things in the world that are, or in the universe, that are very large and very massive, or that are very close together. Really, you need both of these things in order for gravity to be exerted. So this is the gravitational constant, at least in our universe, but you could imagine there are places where it might be much stronger. And for the three-body simulations we're going to do, they just set everything equal to 1 for simplicity. Now, in the meantime, we need to write our compute force function. And when we write our compute force function, that's going to take the body that is exerted upon, the body that is pulling upon it, B2, and that gravitational constant, and it's going to produce an ordered pair, which is this two-dimensional vector that represents the force on B1 that is exerted on B1 as a result of body B2. And to implement this function, well, here's where we get to apply the formula itself. And so we've delayed the detail of needing to know this formula until now. And I will say that we can just go ahead and write it. I'll fill in the details later. The magnitude of the gravitational force is going to be the product of the gravitational constant, and the force of gravity is directly proportional to both the gravitational constant and each of the masses of the two bodies. So the heavier that either body gets, the greater the force of gravity. That makes sense? And as a result, we can say it is this constant, G, times the product of the two masses. But we also know that the farther apart these two bodies get, the weaker the force of gravity. And here is another, one of the great insights from Newton, is to say that you might imagine that there's this inverse proportion. So as two bodies get distant, and in this particular case, I'll say I need another little subroutine that will tell me how far apart are the two bodies. So let me grab the two position vectors that I have of these two bodies and figure out how far apart they are. But actually, as they become more and more apart, the force of gravity becomes weaker at a greater rate. So as a result, what we have here is d times d, or d double star 2 in the denominator. So the force of gravity really drops off, which is why you're not really under the influence of Jupiter. Even though it's massive, it's quite far away from you for its mass, and so you're not being actively pulled by it. That's probably a good thing. So I've got this value of d, I've got the magnitude. I want to make sure that I avoid something really weird happening, which would be what would happen if you have two different bodies, but the distance between them is 0, so we have a collision. In this particular case, I'll just allow them to kind of pass through if they're going in different directions. They probably would have already pulled on each other, but I'm going to return an ordered pair of 0 and 0s to say, let's treat this as 0 force in this particular case. I don't need a weird simulation. And then once I've got the magnitude of this force, then it's simply a matter of, break the force into components. And here's where sort of our first tricky little detail is going to arise, because you might say, f of x is equal to something, and f of y is equal to something else. And at the end of this process, I'm going to return the force as a vector. So I will have whatever it is in the x direction and whatever it is in the y direction. But in the meantime, I need a formula. So the question is, what is that formula? Anyone remember? What should be the question marks? Yeah, this is really the question of, did you have physics? Or did you have physics and did you pay attention in your trigonometry class? Ours is helping us out here. Good. So here's where we get to use a little trigonometry. And I've actually got an image that we can take a look at. And here's where you remember, oh yeah, it's going to be that cosine thing and the sine thing. Which is, if you have the magnitude of whatever this force vector is between two things, and you want to say, what is its value in the x direction, and what is its value in the y direction? Well, we know that if we were to be able to know what f of x is, and we look at the ratio, so if we know this angle theta, then we get a triangle, and here's where our trigonometry comes in, and we say, well, the cosine of this angle, I think, is whatever is adjacent to it, so fx, divided by the hypotenuse, which in this case is the magnitude of the force. And how about in the y direction? Well, we know that the sine of theta is the opposite over the hypotenuse, so the sine of this theta is the magnitude in the y direction divided by the magnitude of the force F. And then you can multiply across. So when you multiply across, you get, well, cosine of theta is equal to the ratio of fx over f. And when we multiply both sides by f, you get that the magnitude of fx is the magnitude of f times the cosine of the theta, and the magnitude in the y direction is equal to the magnitude of the force times sine of theta. And that's good. And that means that we're going to be stuck in having to do something like, like theta equals something. And then we can do this by saying, well, I say it's, when I look again at my components, the x component is going to be the magnitude times the cosine of this theta. So we would say f magnitude times the cosine, math.cosine of theta. And the same thing down here with sine of theta. And I wrote, there was, I think I did a couple of these demos with students in person. And you wound up having to write a subroutine, okay, for computing this theta. Because you had to dig into doing like an inverse tangent and thinking about, all the different directions this thing could be going into, and that giving you positive x's and negative y's in all the different cases. And it was hideous. And then a student said, why are you doing that? Why would you do it that way? And I said, well, that's what they teach you, that the force in the x direction is the magnitude times the cosine of the angle. And he said, but we don't need the cosine of the angle because we know what the cosine of the angle is. And I thought, why? And then he said, well, you know what the distance is. There's 2 points here, and you know what the distance is, and you know what the delta x is, and you know what the delta y is. So you're thinking about everything in terms of the force, but I actually know what the positions of the 2 bodies are. So I know what cosine of theta is. And that's because, well, cosine of theta is the adjacent over the hypotenuse. So it's just delta x over d. And sine of theta is just the opposite over the hypotenuse. So it's just the change in the y values over d. And I was like, yeah, why have I not been doing that the whole time? And it made this demo way, way easier because I can just figure out what cosine and sine of theta are without actually needing to know what theta is. And that makes things a lot simpler. So I will say, yes, I'm going to still have times the cosine of something, and I will still have f magnitude times the sine of something, but I'm not going to need to call these. Instead, I'm going to say cosine is equal to something, and sine is equal to something else. And the cosine in particular is going to be equal to, if I look at my drawing, it's equal to the change in the x values divided by the distance d. I already computed d. So when I look at gravity, I'm going to say, well, what is the change in the x values? It's b2 dot position dot x minus b1 dot position dot y. And then I'm just going to divide that by d. And it's that easy. And then the sine of the angle, if I look back at my picture, is the change in the y values. So look at B2. And look at its y value, subtract B's y value, and then divide by D. So what's the change divided by D? And if I come back over here, I'm going to say B2 dot position dot y minus B1. Or did I call it B? No, I called it B1. B1 dot position dot y divided by D. And here's where we had the question, well, what if D is 0? And here's why I made sure to go ahead and handle that case. So if D is equal to 0, I've already aborted. And you can see here's why I've made that decision, because things are going to get really weird very fast if I don't go ahead and handle that case. So now instead of times math dot cosine of theta, I just say times the cosine. And now here I'm going to say this is times the sine. And now my function's finished. I didn't have to worry too much. And that's pretty good. Of course, we probably need to go ahead and write our distance function too. And so if we're going to write our distance function, here's where we could say, well, in order to compute the distance, you probably do know the distance formula. If we look back at our picture from before, and you want to know what's the distance d, well, you've got a right triangle here. So d squared is equal to this thing squared plus this thing squared, so we can just take a square root. And we can say we want to return, well, I'll say dx is equal to, in this particular case, I have 2 positions. So I have 2 position ordered pairs. And it doesn't matter which direction I do this in, but I'll do p2.x minus p1.x. And for dy, I'll do p2.y minus p1.y. And then I want to square these two things, dx times dx, plus dy times dy. And as the result of that, I want to take the square root. So I've got math imported, and here we get to use it. BZ, you say, I wish you understood math better. Yeah, me too. Me too. The problem is when you don't wish you understood math better. I mean, I've got a PhD in math. I feel like I hardly understand it at all. What is it Einstein said? Don't worry about your struggles in mathematics. I assure you that mine are far greater. That's true. I think it becomes truer for me every day, but that's another conversation. for now, we've written our copy universe function. We've got our distance function written. And so the copy stuff is done. The force computation stuff is magically done all of a sudden. As is often the case, we know we have well-written code. If we get to the bottom and we're like, oh yeah, we're finished. So we have this little distance function to clean up, but we've written it. And so then it, if we're thinking through what is there remaining, we have, if we look at our update universe function, we've actually handled all of the update acceleration, which had a pretty deep collection of subroutines that it called. And that's not going to be quite the case for update velocity and update position, because we've done the hard part. We've actually produced the engine of the gravity forces. And so we just need to update the velocity and update the position. So let's look for we've got update acceleration there. Update velocity is going to be here. Let's do it first. And it turns out that we obtain a slightly more accurate simulation for complicated reasons that we're not going to get into. If I say, what is the velocity after I add a little time step? It's to say, what was my previous velocity? So far, so good. And then I will say, a lot of times you might say, I'm going to look at my current acceleration, or should I look at the previous acceleration? So this is the acceleration of the body in the previous time step. This is the acceleration of the body in the current time step. And the Verlet formula says, average these two things together. So this might look complicated. All this is doing is averaging the previous acceleration and the current acceleration. And once it does that, it gets this average acceleration value. It multiplies it by the time step. So here's where we get to apply our kinematics formulas that indicate, well, when you're estimating the change in velocity or position or something, it is whatever your acceleration value that you're using, which here is going to be an average, times the time step. So this is our current velocity, and this is the contribution as the result of the pull that we have of the force of gravity. And as you might guess, we're going to do this in the x direction, and we're going to do it in the y direction. But the hard part here is trusting this formula. Once we have this, there's not really a whole lot to do. We're just going to say, well, the x component is going to be something, and the y component is going to be something, and then we're going to return an ordered pair corresponding to Vx and Vy. And then in the meantime, I'm going to say, all right, well, what is it that we're doing? I'm accessing the current velocity of B in the x direction, and same thing for the y direction. And then I'm going to add in the contribution from the force of gravity, which is this stuff. And here's where I'm just going to say, well, we have 0.5 times b dot acceleration in the x direction plus the old acceleration in the x direction. And then here's where we actually get to use our time step. So when we saw this, here our time step is, we called it delta t in the doc string. And we're going to have the exact same formula in each case, but I want to make sure I'm very careful. So I'm always careful with copying code, but I'm doubly careful if I'm ever making a very slight change to say I need to make that change there to a y and this change there to a y, and then I should be in good shape. And that's the entire function. And so then it's simply a matter of taking, what is the corresponding set of formulas for updating the position. And the formulas are just a little bit longer. So in that particular case, when we update the position, we have the body that we want to update. We have the previous acceleration ordered pair vector that we have. We're also going to look at the previous velocity too. And here, again, for reasons that are a little bit beyond what I want to say, the position at the new point, you might say, does this new velocity affect it? And the physicists would tell you, you get the most accurate approximation here if you say, well, it's the previous position, but then you say, look at the previous velocity, and say you haven't had really enough time to update your velocity enough to factor in here. So we're going to take whatever your velocity was beforehand, multiply. So think of this as speed. Multiply it by the amount of time that you travel, and that's going to give you how much distance you traveled, at least in the X or Y direction. And then you have this little additional factor that comes from the force of gravity and the acceleration that you have. So the velocity is also changing over this time period, and that's because of the acceleration value too. So you might be accelerating positively or negatively, or in whatever way that this is changing, this additional term factors into the fact that the velocity might be changing too. So fortunately, if you've had a physics class, you'll have seen this until you're bored to death. But we get to apply this formula, and it's the exact same thing. This formula, once we know it, is very easy to apply in terms of code. I'm just going to say, well, we have px is equal to something. We have py is equal to something. At the end of this, we're going to return an ordered pair whose two attributes are equal to px and py. And here's where we apply the formula. So px is equal to whatever the current position of x is, plus, if we look at the formula, we see the old velocity times the time step. And that's it for that. I probably should say old velocity in the x direction though. And then we take 1/2 of the previous acceleration in the x direction. And we multiply it by the time squared. So I could do time double star 2, or I'll just do time times time. And so here we have, this is where it was. This is the contribution from its previous velocity, and then the velocity is changing. So due to the force of gravity, we need to adjust it a little bit. Again, I will copy it, and I will be careful to say every time I see a dot x, I need to make this a dot y. And now we have a final update position function too. And lo and behold, as you look through our code, just as we saw before, we're at the bottom of the function hierarchy, so to speak. And we've written every function that we need for our physics engine, which is pretty cool. So as a result of this, even though we wrote our own deep copy functions, and even though we've got really long doc strings and a few places where we actually perform parameter checks and all this sort of thing, we have a collection of code here that's 250 lines long. Functionally, the code is probably like 150 lines or fewer, even though our code is very steady. And so we've now produced something that can simulate the force of gravity for literally any collection of bodies that we give it, as long as we're patient enough to let it run. So that's what we should do. And we now can go to our code, now that we've written all of this, we now can go to our code in main.py. And here's where I want to run the full pipeline. So I want to read a universe from file. I want to simulate gravity for however many generations. I want to render all of these to surfaces. And then I want to encode all these frames to a video. So I'm going to take this as command line arguments. It gives us an opportunity to practice what we have done with command line arguments already. And so let's say we expect 5 command line arguments. Okay. And the first one is going to be, in this particular case, the scenario name. So that's like Jupiter moons or butterfly or whatever it is that we're going to be simulating. We're also going to have the number of generations that we run. We're going to have the time step in seconds. And we're going to have also the canvas width in pixels. As you remember from drawing, that winds up being useful, because that tells us how wide to draw the canvas. And then we're also going to have a this drawing frequency that tells us how often we render a frame for a snapshot. Okay, so we should read all these in from the user, and if there aren't the appropriate number of command line arguments, we probably should produce an error. So remember that the there is a sys.argv of 0 that's just going to be the name of the file. And so I want to check and make sure that this array that I have is equal to 6. If it's not equal to 6, I'm going to be very strict and raise a value error and say error, incorrect number of command line arguments, 6 are desired. Okay. And if I make it here, I know that there are exactly 6, so I can go in and I can access the ones that I care about. So the scenario, which is going to be reading in from the file, is going to be sys.argv of 1. And it's a file name, so it's going to come in as a string. We know that sys.argv is going to be this collection of strings. And so I don't need to parse it at all. What we will need to parse is when we access the command line arguments corresponding to like the number of generations. In the meantime, I'm going to establish the input file and the output prefix. So I'm going to have a couple little F strings. So the scenario here is like, e.g., Jupiter moons or butterfly. Okay. And as a result, if we look at like our data, our input file is going to be data slash whatever that scenario is .txt. And so I'll say that the input file here is equal to an F string of data slash, and then I'm going to give it the variable name scenario .txt. And I want to write to a video path that is also an F string that is output slash the scenario, and in this case .mp4. So everything's going to go into this output folder that's currently empty. Then I want to parse the remaining arguments. So I want to say numgens is equal to the next thing. So that's sys.argv of 2. Except the number of generations here should be an integer. And so I'm going to parse it from a string to an integer. Then we're going to have time step. And that time step is sys.argv of 3. And the time step is going to be very much a float. So that'll be a decimal. The canvas width is going to be what happens when I read in the next parameter, which is going to be in pixels, which means I need an int of sys.argv of 4. And then I need the drawing frequency, and that is, again, very much an integer. That will be sys.argv of 5. And if we make it here, let's get in the habit of printing a message to the user to say, hey, I read the command line arguments. And at this point in time, then we can start our simulation. So if we, I start our pipeline, I should say, the first thing we want to do is to read in my universe from file. Then I'll simulate the force of gravity. Then I'll write all of this to Pygame services and draw them. And then I'll encode all of that into an MP4 video. So let's read the initial universe. And we know where it needs to be. It's that input file. And here's where I'll say that the initial universe that I care about is equal to, and I've got a bunch of stuff imported for us. So fortunately, I've got like read universe imported from the IO file. I've got animate services imported from this animate.py file that I've got, and I've got the drawing stuff imported. So if I ever need any of that, it's already imported for me. And this initial universe is going to be the result of reading the universe from this particular file, which is that input file. That's what we called it. Then once I've read it, I'll say, well, universe read successfully. Let's give it an exclamation mark. That seems like it's pretty good. And at this point in time, we're going to say, well, let's simulate the force of gravity. So the first thing we do is run the engine. And to run the engine, I'll say, well, what do I care about? I care about having a collection of time points. Each of those is a snapshot of one particular universe object. And I'll say that's the result of simulating gravity of the initial universe for the number of generations that I care about and for the time that I care about. I called it, in this case, I called it time step. I think I called this numgens. So that's why it's not being colored correctly. If I make it there, I'm just going to say, well, the gravity simulation is complete. Again, let's give it another exclamation mark. Now it's just a matter of saying, I've processed the command line arguments, I've read the universe, I've simulated gravity, and I want to render these frames to surfaces. Then I want to encode them as a video. In order to do that, we'll say, all right, well, let's say rendering frames to surfaces. And here's where I will say surfaces is equal to animate the system of the time points, the canvas width, and the drawing frequency. Okay. Here's where this animate system function comes in from drawing. So if we look at drawing, we'll see that we have a definition animate system. And this is where it takes the collection of universes that we have, the width of the canvas in pixels, and the drawing frequency. And it goes through and figures out if these are the positions of my objects, where on the canvas do they need to go? So it provides a scaling there. And it only actually produces a surface if the current index is divisible by that drawing frequency. This is what we saw at the beginning when I walked us through, what's going on with this drawing.py file. So I get to call that function now and say, I give it the universes, I give it the canvas width in pixels, and I give it the drawing frequency. And as a result, I get the surfaces. Once I've got the surfaces, I'm going to say, well, frames drawn, and that's finished. And now I go to the fourth and final part of what I do, which is to say, I'm going to encode the video. And I will call animate surfaces of, this all comes from animate.py. Animate surfaces takes this list of surface objects that I have that I've drawn on. So these are our objects that we think of as virtual canvases. And it takes the video path that I care about. It doesn't return anything, and it simply writes an MP4 video to that video path. So we've seen this before in the context of drawing other things. And now I can apply the same thing. So animate surfaces is going to take the surfaces that I just made, and it's going to take the output path that I cared about, which in this case was called video path. Once I have that, I'm going to say two things. Video produced. And if I make it here, we've accomplished something. And I'm going to say animation is finished and exiting normally. That should be it. We've produced our big simulation. All that remains is to give it some command line arguments and see if it works. So let's start with a simple example. I mean, I'm a little worried. Do you think it's going to work? What's your confidence that I'm not going to have some awful bug, 0 to 10? I make it look easy? Oh, thank you. It is easy, and you can do it too. The real problem is that this particular skill is both still very useful and also dead. Like, it's the irony of our era that knowing how to do this is extremely transferable to solving things in other contexts that are not this. But doing this specific thing can be done in AI, with AI in like 0.01 milliseconds, So that's always a strange thing to think about, that the AI could just give you this code, but you wouldn't learn anything. But knowing how to do this also makes you better at using the AI. We're in this very, very odd era in which like old skills are useful to learn the new things, but the new things are not as practical as they used to be. I don't know. All right. Everybody's confident. That's good. Anybody who'd answered under a 7 I was just going to ban from the channel forever. So that's good. You made the right call. And I'm going to run this. So let's figure out some command line parameters for us. I don't know what I did here. Let's clear this thing. Okay. What have I done? I have no idea what I've done. I want to go to the terminal. What? CSH. Okay, there we go. I don't know why I was selected on Python. All right. You said you thought I knew what I was doing, and now I don't. All right, let's go to the terminal. Now we get to apply this to a real thing. And the real thing is, let's look at, we've got, our command line arguments are the scenario name. So let's do it for Jupiter moons. And I'm going to say Python 3 or Python on a Windows machine. Main.py is the file I'm running. Then I'm going to say Jupiter moons is the prefix that I care about. And that's going to go in and read it from the data folder, but then draw it to output. And then the number of generations. And let's not do this for a bunch. I don't know. Let's do it for 500 or something. Then the time step in seconds, I'm going to give it 60 seconds. So it's a minute. So I'm updating the moons of Jupiter every minute, which you think that's a pretty small unit of time. That should be pretty good. And then let's make the canvas 1500 wide. And let's make it so that we only draw every 10 frames. So every 10 minutes, I'm going to draw it to a canvas. And now I'm going to hit enter and we're going to see, is it going to work? No such file or directory. Okay. Can't open this. No such file or directory. Okay, that's because we're a little bit into this. And what did I forget to do? Of course this isn't going to work because I didn't cd and src/gravity. All right. Now, I'm going to try it again. Python 3. Actually, I'm going to hit the up arrow 2 times. So it's going to take me back to this. And now I'm not going to look. I'm going to hit enter. Oh, body has no attribute acceleration. Did you mean acceleration? Okay. So at least we're on understandable stuff. Acceleration. I think it's because I'm fluent in Italian. So I think that's how it's spelled there. All right, what line is this? 134 and update velocity, gravity.py, and... Ooh. Well, at least it's the same in each of these. I copied it well. All right, that should be good. Let's try it again. Okay. All right, that was quick. So I ran it on a small case, and let's see. So Jupiter moons got output. Okay, I see Jupiter, and I see 4 tiny moons. In practice, they're actually much, much smaller. So let's see what happens when we play. And they appear to turn, which is good. So if they're turning, the next thing I should do is to run it for more generations. So let's keep the time step at a minute. Let's keep 1500 as the canvas width. And let's keep 10 as the number of, that seemed reasonable, but I want to make this much higher. And it's nice because for 5,000 steps, I mean, I know Python's slow and terrible, but it did pretty good. So it's taking a little bit of time to run. And that's because I have 500 frames here to encode the video. It's going to take a little bit of time. Finished, and let's see. Oh no. Oh dear. So this one took a big right turn. This one appears to be okay. This one, everything was going okay, and then it just decided to just depart. Ooh. Ooh, this is going to be a fun one to debug live. I don't know. I don't know what I did. I have no idea. Now, there's a very easy fix here, right? Which is to go and test all of my individual functions. I mean, and make sure I have debug data sets for them, and make sure that they're passing all of this, and design a bunch of tests. That's absolutely what we should do. We also could go to Cognitera, where we've written all of those before. This would be a good use case for it, to see which of these functions is going to fail. Or we could do the most fun thing, which is just to stare at our code and pray and hope everything works out. What should we do? Make sure that I've got, this is every 10 frames, 1500, 60, and 5000. It's not going to be this, but scenario, number gens, the time step, canvas width, and the drawing frequency. Did I put X in both lines? So remember, I told you to be very wary of this. That would be my guess, is this is so bizarre. Like, you see how they start to turn and then this one decides to just not? It reaches a point where just something weird happens. That weirdness is probably, the result of, in one of my physics functions. Vitor, thank you. It's probably that I didn't practice what I preach and said, when I said be very, very careful when you copy stuff. Make sure that you don't do something weird. Oh my goodness. You see my point? Like, this is the type of thing that is, you would never, this is why you don't debug code by staring at it when you go to a project that's this large. And in this particular case, that's all it takes. So let's try this one more time. And I might still be wrong. And the point is, I'm not going to panic, because at the end of the day, I could have taken each individual one of my functions. Fortunately, we went through the process of writing test data sets for every single one of these functions. And so we could go and test them in our auto graders. So that's what good code is. It's not to just pray that the chat helps me out. But in this particular case, they did. Thank you. And now I get to see, is this going to be a disaster again? Because it was funny, because it looked like it was working. It's going to take a second. The best part is you allow me to fail. That's how I know you like me, is you allow me to fail. All right, now we're going to see and hope they curve. Okay. All right, nothing weird from now on. All right, good. And there's a lot you could do with the visuals here, right? I might post code for this that has trails that actually fade out as we go through it, right? Because this is saving the trails for too long. One of the things that's nice, though, is what you can see is this is not a perfect circle. And the question is, why is that? Why is that not a perfect circle? No one gets to ask me which moon is which, by the way. Why do you think this is not a perfect circle? Great guess, because of the influence of other bodies. Guess one that's great. That might be it. I'll give you a hint. Jupiter is a lot heavier than all these moons. So then they're in stable orbits where they're really not affecting each other tremendously. Option 2, they never are perfect circles. That's right. That's true. BZ, you're right. They're ellipses. They're ellipses, but this is also not the same ellipse. So if it's in a stable orbit, it will be the same ellipse over and over. So we don't quite have the right answer for this yet. quite have the right answer. And I'll give you a hint. If this could extend, you see that this isn't going to form a perfect circle either, or ellipse. It's not going to come back to where it was. And should it come back to where it was? Yeah, I mean, there may be influence each other a little bit, but this one and this one probably should cancel each other out. Lori, great, good job. Our simulation is not fine-grained enough. What does that mean? It means when I run this simulation, I updated it every minute. And you might think that's enough, that's plenty. But if we really want an accurate simulation, we need to update this thing much more frequently. So I could, for example, what could I do? I could lower this to not 60, but say 0.6. That would drop it by a factor of 100. If I drop that by a factor of 100, well, I need to update this to have a greater factor of 100 because that's the number of time steps, the number of generations. So to get the same picture, I want to have 100 times the number of steps, and I'm going to have each one be 1/100th as big. And then I want to make definitely sure, because otherwise we're going to be here until next year, that when I say I want to make sure that when I draw this thing, I see the same thing, I want to add a factor of 100 to that. So everything else stays the same. And by that I mean just the parameters, Jupiter moons, and this 1500 canvas width. And now when I run it, let's see how long it takes to simulate the force of gravity for 500,000 time steps. We'll have to wait a little bit, but it's not going to be too bad, I don't think. Hopefully it's going to be worth the wait. We'll see. We know that the drawing part of it is going to take the same amount of time. So gravity simulation is finished. We have the same number of frames because we're ranging through all of these, and we're being very stingy about when we actually render a frame to a surface because I'm only doing it when it's divisible by 1,000. So hopefully this won't take too long. I think it's doing a lot of ranging. And it's keeping track of the trails. So it does have a little bit of work to do here. I think there's probably room for making our simulation run a little bit faster if we ensure that the trails are also only drawn every 1,000 generations, which that might be the case. Maybe I've done this to multiplying by a factor of 100 was too much. I'm not sure. We'll see. I'll give it a few seconds. If it's not going to work, then we'll always reset and do something in between. I'm confused by that. Drawing frequency. Just seeing if there's anything here that would imply. Yeah, this is our issue. So we're only actually appending to the canvas when it's divisible by drawing frequency, but we have the trails. It's doing a lot of work here because this trail frequency is set equal to 1. I'm hesitant to change it too much. Yeah, I need to clean this up. Good news is when we post the code, it's going to be faster. All right. That is going to, it's probably the thing that's almost done, but for now, we've added a lot. So I bit off a lot more than I wanted to chew here, and instead, let's see what happens if I just take a middle ground of every 6 seconds and every 100 frames and 50,000. simulations or generations. So gravity simulation is complete. Now it's rendering all those frames. This should be quite a bit faster. And then we get to look at three-body simulations. They're even cooler. So we drew the frames. We're in the video encoding step. All right, now we get to look at Jupiter moons again. Now what we hope we see is the same simulation. So if we got it right, we're going to see the same pace of simulation. And you could go and multiply out and see, how long are these actually? Here's another fun question for you to post in our Discord. How long are these orbits taking? Right? Can you figure out about how long each of these individual circles takes based off the parameters I have? Is the circle going to complete? So we might have a little bit of a difference. You see how much tighter this is. So we lowered this by a factor of 10. We went from 60 second to 6 second simulations. Things got better. So yay, we won. But the moons of Jupiter is pretty boring because there hasn't been a great disturbance, I don't think, to these orbits in a really long time. And they're all pretty much just proceeding in circles or ellipses. Now, let's introduce a little bit more anarchy to this. And yeah, how could beyond making the equations wrong, what are the types of things we could do to ensure that our code is able to handle weird cases? What if I were to go into Jupiter moons and I made this roughly half the size? Okay, and I'm going to run this, and in the meantime, I want you to tell me, remember that's a 6. I want you to tell me, what is this going to look like? That's my question for you. When I render this, and I've made the force of gravity half as big between any two objects. So what's actually going to happen to our simulation? When I visualize it, what will actually happen? Any thoughts? No thoughts. No thoughts from the chat. Okay. Moons will go further away. It's as if this force that was holding everything together is going to release. Okay, let's see. So you might think that they're never going to come back, right? But definitely the force has weakened. So this pull of Jupiter on each of the moons is not as strong as it could be. And the question is it going to be strong enough to retain these moons as they fly away? The answer is yes. I'll advance it to see that in this particular case, we've made the force of gravity pretty weak. So it's going to take a while for all of these moons to come back. Again, play around with this. Post cool visualizations to our channels. Do whatever you like. The real question is, what happens if I made it like twice as strong? So if I went in here and instead of that being a 6, I don't know, I made this let's get really anarchical and multiply it by a factor of 10. Then when I run this, what's going to happen? Force of gravity got stronger. Collapse onto the planet is a very, very dark thought. You think the force of gravity becomes strong enough to take these things and just pull them in? Well, they're definitely going to get pulled in. That's true. But they also have a lot of inertia, which is good. Maybe we have collisions. Yeah, maybe it goes into the planet. So this is not the sort of thing that we've actually written in, but I don't think you expected that, maybe, that it would get slingshot out. This one might be really faded, okay? And so what you see here is this one probably has the most believable orbit, which is that it becomes an ellipse. It's still going to be an ellipse, and this we're not going to probably see it long enough. So it's actually still tracking all of the bodies, but they're not within the frame. So we'll see if any of them come back. Hey, it came back. See, I promised. They are going to come back. So it forced all of the orbits to go into a more elliptical shape, which is pretty cool. I mean, this is, I don't know. I could play around with this all day long, but I'll show you what happens if I make this back to 11, but I make this like a 12. Okay, so I multiply it by a factor of 2. You're going to see something kind of in between these two extreme cases. So our hypothesis is they will be ellipses, but they'll be between the circles that we saw and these very elliptical orbits. Very elliptical, I think, is the wrong term. I think very eccentric is the technical term. So it's surprising because they get pulled in so hard that they're slung outward. And what's neat about it is it's an example of changing one parameter, one tiny parameter, this whole thing. And we just trust all the equations to work. And they just do. Now, that previous simulation, things got so weird that I don't think I would accept it as like gospel, because here's where our, something like this value of 6 seconds. 6 seconds might make a huge difference between an accurate and an inaccurate simulation, but here's probably the case of having, just multiplying the force of gravity by a factor of about 2. And you see they're not circular, but they're still going to get pulled into stable orbits as long as they don't collide. And the likelihood of a collision is really tiny. And you see you're probably going to about complete the circle. You see how quickly the inner moon already had a stable orbit. And you could do a whole lot of other stuff with this. I mean, you can compute all these different points in orbits where certain things happen and add multiple bodies into it. So I've always thought there's a lot that you could do with this, but what I want to do is look at some of the 3-body simulations before we wrap up. So I'll take that back to a normal value. And then we will wrap up, but I want to show you, let's do Python 3 main.py. And what's a good one to start with? Let's do figure 8. And I'm going to do it for 100,000 generations. And I'm going to do it for 0.0001. And 1500 is the width. And 300 is the frequency that I'm going to do it. And hopefully that should be good. It might take us a little bit of time. The gravity simulation is going to be quick. It's doing this rendering behind the scenes. So this will be worth waiting on. Lori, I feel bad that I know the exact Star Trek, the slingshot effect reference that you're talking about. Maybe I shouldn't feel bad. Okay. Now we're going to look at the figure 8. So here's a 3-body simulation where you have 3 bodies, and I'd say the orbits are not tremendously chaotic, right? So they're just following this figure 8, and the blue one's trail seems to be dominating here. That's something we could look at in terms of adjusting our simulation, but as a result of this, you get this nice stable collection of orbits where they're influencing each other, but they're not going to collide, and they're always going to follow this figure 8. Now, has that been observed in heavenly bodies? Absolutely not. But let's look at a couple others. So let's look at Python 3 main.py, and I'm going to change, actually I'm going to go up. I'm not going to change any of the parameters here except for, I don't want to do figure 8. I want to do, let's look at moth, And then I'm going to look at one more, which is called yarn. And so the question is, why people were looking at this is, if the three-body problem is a hard problem to solve, can we find really weird examples of simulating three bodies where they actually form periodic patterns and orbits? And it's really impressive. I mean, this one's cool enough, but it's really impressive what people were able to find at a pretty early era of computing. And so let's see. So here's moth. I think you might be surprised at some of these and what they were able to identify and be able to establish that these are in fact periodic. So if you do your simulation with a small enough time step, you'll see everything eventually, iterate back on itself and come back to its initial starting position. So there must have been a huge amount of work in order to do this, right? And in the meantime, I'm going to run one more, which is called yarn, and then we're going to wrap up. I'm going to show you the coolest ones. Well, they're no less cool than this, but some of the coolest ones require a very tiny time step and us running them for a lot of steps. And so I don't want to do that live, but I'll show you the results here, where I happen to use maybe a language that isn't quite as slow as Python, hint, hint, in order to produce these, since I'm going to need a lot of time. Okay, so let's look at yarn. We'll take a look at it. And it's kind of in the similar sort of family as moth. And then I'm going to ask you a couple questions. So here's yarn. So if I run butterfly or dragonfly on this same collection of parameters, these are amazing, but what is going to happen is two of these objects are going to get too close to each other. And so they're not going to collide, but they're going to slingshot each other out. And you have to have a very, very tiny time step in order to make sure that that doesn't produce a simulation that sends something in slightly the wrong direction. And that actually is tight when they get close to each other. It slingshots out, but it's also able to make very rapid computations. So I'll show you what happens here. What happens when we run it on these parameters for something like this is they get really close to each other, and as a result, this is not quite right. So it's going to fly off the screen. Eventually it's going to come out, and then we have this issue. So this is where the distance between them didn't hit 0, but it got so small that it wound up just flinging them out. So that force of gravity between them became very, very large because it's inversely proportional to the square of the distance. So that's not good. So here's your task. Go and run this and optimize it and run it on a lot larger number of steps and a smaller step size. In the meantime, I'll show you. It's going to be too big. Let me show you. Here's one that's going to work. So here's Dragonfly. And that's pretty cool because you saw the red and green thing came so close to each other that it actually seems like they've touched. They didn't in fact touch. It's just a representation of that when we were drawing it, they got that close to each other. So that's really cool. And what's also neat about this is how the blue thing gets flung out and then comes back. And then we're also going to have, here's the butterfly. This is the one that didn't quite work before. And now you're going to see these tight slingshots, but the slingshot's always going to get close to another planet enough to then slingshot it back. So I don't know which one of these is your favorite. They have found dozens and dozens of these very strange, but nevertheless, I think periodic 3-body simulations. So I would not want to live in any kind of solar system that exhibits this, but look at how neat this is. I mean, it's amazing. So you go and take our simulation, improve it, see if you can make that. I'd love to see it in the Discord. Our simulation is pretty cool. It also suffers from a flaw, and the flaw is in any language, even Python or even a very fast language. It's not going to scale very well. In particular, as the number of bodies gets big that I'm simulating, it's going to scale very poorly. And there's a reason for that. You might think about it for a second. I'm going to tell you what it is, which is that when I compute, when I update the universe, this is, right now it's fast because there aren't many bodies. But when I update the universe, I update this acceleration. These two are very quick, right? Each of these is just for each body. But when I update the acceleration, I do this for every body in the universe. But then when I call update acceleration, I also, which computes the net force. When I compute that net force, how does it work? It then ranges over all the bodies in the universe too. So if you have n bodies in the universe, as a result of this, you wind up with about n squared different force computations. And you might not think that's a big deal, but why that's a big deal is if I were to do I saw people asking in the chat, what if we did like a black hole? Okay, well, you have a dark mind if you want to do that. But what if we did something like my dark mind says, what if we make 2 galaxies collide? So I'm going to have tens of thousands of stars and make them collide. The problem is if I have 100,000 bodies, then I want to compute the force of everybody on everybody else. And so now I've got to do 100,000 squared total force computations, and that's for every single time step. And so that's going to cause the runtime of this thing to blow up. And as a result, it turns out that we can do something amazingly beautiful. And it's the subject of one of our collection of practice exercises that we have for you. We can do something amazingly beautiful to speed that up, because it turns out things are, if they're far apart from each other or not very big, they're not going to affect each other much. But then it's kind of a chicken and the egg, because you say, well, how do I know very quickly what's close to each other and what's far apart? And it turns out that the way to answer that question is going to, 1, require more object-oriented programming, and number 2, the answer will lie in making a tree out of all of your bodies. That might seem strange, because we're going to look at making a tree in a biological context to make like the tree of life. But it turns out that you can make this simulation way faster, and you can look at an even more amazing simulation where you're looking at tens of thousands of things interacting with each other. But you have to know more about object-oriented programming. You have to appreciate how the tree works. So that is what we're going to save until next time. And I'll see you then. But until then, happy coding.